The third topic in this mini course on the zoology of excitons is Frenkel excitons, a brand new species, if you want, of excitons compared to the Wannier ones that we talked about previously. And the most important example of Frenkel excitons are excitons that are localized on a single molecule. And I'll make the case that I guess single organic molecules in organic semiconductors are really, really important examples that you'll find, for example, in OLED screens and organic solar cells and other interesting optoelectronic devices. And so what we're going to do today is essentially give an overview of the molecular language that you use to talk about Frenkel excitons in most cases. We'll talk about Singlet excitons, Triplet excitons, Davydov splitting, and we'll describe how to make Jablonski diagrams to essentially reference the energy of the different types of excitons. And I guess our case study here will probably be the molecule tetracene. So a lot of what I'm going to talk about today is coming from the book Organic Molecular Solids by Schwerer and Wolf. So I have that here, and picture on the slide. It's a really good book. Maybe doesn't have completely up-to-date, state-of-the-art about organic molecular solid applications, but is very good basic material. And again, then I guess if you're a chemist and you've taken physical chemistry, you would probably see a lot of this material in your standard physical chemistry textbook, where you talk about molecular spectroscopy in some detail. So Atkins, I think, is the standard there. So here's a picture of an organic semiconductor called anthracene. That's 3 fused benzene rings. And so you have a molecular framework that's held together by carbon-carbon single bonds that are considered as sp2 hybridized, and so you make sigma bonds by the sp2 overlap. And that's sort of the structural framework of the molecule. Oops. And then when you have that sp2 hybridization on each carbon atom, you have a leftover pz orbital. So those look sort of like this, where I just overlaid pz orbital shapes on each of the 14 carbon atoms in the anthracene framework. And these electrons in the pz orbitals that are left over can essentially delocalize over the whole molecular framework and make an extended pi orbital network. And that's like the characteristic feature of a typical organic semiconductor, that you've got this sort of extended pi network that describes the lowest energy excitations in the molecule and the molecular solid, if you're interested in that, which I am. And so then the idea is, within that pi network, you imagine the lowest excitation going from the pi, say, bonding orbital to the pi star anti-bonding molecular orbital. And if you do that, what you've essentially done is to create an exciton on a single molecule. So that's the sort of intuition about Frenkel excitons, is that if you've got a really tiny molecule and you make an excited state, say between the pi and the pi star, the excitonic effects are all trapped on a single molecular entity. And so a Frenkel exciton is often essentially synonymous with a molecular exciton, though not necessarily. Frenkel is a little bit more of a generic word for sort of small. And so this is our map of exciton binding energy as a function of exciton size. And mostly to date, we've been talking about Wannier excitons, so the canonical gallium arsenide exciton. And then we did a case study where we talked about molybdenum disulfide in both bulk and single layer form, and how even though it's still a Wannier type exciton, it's got some interesting features in terms of its binding energy compared to, say, gallium arsenide. And these are all situations where the average spacing between the electron and hole that make up the exciton is much larger than the typical lattice spacing A. And so in the Frenkel case, we go to a situation where this is violated. And the exact boundary between Wannier and Frenkel is not rigid, right? There's not a strict exciton size that absolutely delineates between these two cases. But roughly speaking, if the average size is comparable to a lattice spacing or not much bigger than a lattice spacing, you're in a Frenkel exciton regime. And this is a fairly broad regime, and the blue thing here is meant to indicate the vagueness of the boundary. So Frenkel exciton, our first case is going to be like an acene, like anthracene or tetracene, where we have the size of the exciton that is not much greater than the lattice spacing. Now this dashed black line is meant to indicate when the average size is exactly equal to a lattice spacing, and so Frenkel excitons can be maybe 1 or 2 lattice spacings in size. The size of the exciton on a single molecule of, say, anthracene is probably a bit bigger than the lattice spacing, right? Because the lattice spacing is determined by sort of pi-pi stacking between adjacent molecules, and for a long molecule that may well be smaller than the actual size. As we go on in the mini course, we'll be looking at precisely this dashed line and even some circumstances where the size of the exciton is smaller than the lattice spacing, and those are really interesting species of exciton where we can sort of expect some novel properties. So how do we know that there is such a thing as a Frenkel exciton or a molecular exciton? And the way we do it is we compare gas phase or dilute solution phase optical spectra with solid state spectra, right? And the idea here is that if you've got a molecule in the gas phase or in a very dilute solution, by definition, its excited state properties are just those of a single molecule. And so if you then go and take that material into the solid state and the optical properties are not dramatically altered, then that's evidence that there is such a thing as a Frenkel exciton, namely an excited state in a solid that is predominantly localized on a single molecule or a single, unit. And so now we'll go into our case study of tetracene, which is just anthracene but with an extra benzene ring fuse. So instead of 3 benzene rings, it's 4. And there's just actually more data for tetracene. It's this beautiful orange solid. And it's really easy to get very high quality optical data on that particular organic semiconductor. And so this is from a paper. The reference is here, Yamagata et al. And so this is a picture of tetracene in solid state form. And so you've got this fairly long acene molecule, and then you've got, lattice spacings like from here to here that are sort of the pi-pi lattice spacing where they're sort of displaced with respect to one another. But the thing that I want to point out to you is that in the solution phase, where you just dissolve some tetracene in whatever, octanol or something, I don't know what they dissolve it in, I forgot. But you can dissolve it in a lot of different things. You see a series of peaks that are these dashed lines, and we'll come back to what we mean by 0001 in just a few slides, but in the solution phase you get this series of peaks, okay? And then in the solid state, what happens is you get almost the exact same series of peaks displaced to a little bit lower energy and now slightly polarization dependent. So the black curve is polarization of light parallel to the B axis of the unit cell, and red curve is polarization perpendicular to the B axis of the unit cell, so along A. And so you get basically almost replicas of the solution phase spectra, 1, 2, 3, 4 peaks, 1, 2, 3, 4 peaks, shifted in energy and slightly polarization dependent. And so the argument is that because the energy positions are very similar and the sequence, the relative intensity and the spacing of these peaks is almost identical to the solution phase, fundamentally this is an optical property that's determined by excitations on individual molecules. So Frenkel or molecular excitons. And that's sort of the long and short of it. That's how we know that such a thing exists. So we do from this conclude that tetracene is a so-called molecular solid, and aggregation in the solid state makes relatively minor quantitative changes to the optical properties. There are minor differences. So we do see that all the peaks shift in energy by a little bit. It's not a lot. And then this polarization effect is pretty interesting. The fact that there's a different energy associated with polarization is a unique solid state effect, and this will be the Davydov splitting that we'll come to at the very end. And then finally, the fact that there's a series of peaks, not just one absorption peak, is also important, that we'll come to again in just a few slides. So the differences are minor, but I guess what I want to say about this series of peaks is that is actually further evidence that this is a fundamentally molecular exciton, right? That's the vibronic progression that tells us we're really looking at something that is associated with a very specific molecular structure that hasn't changed much in going from dilute solution to condensed solid state. Let's do some rough calculations, because a big part of this course is like, yes, we have this diverse zoology of different types of excitons, but we have sort of a core intuition that comes from the hydrogenic model, right? And so let's see what kinds of things we understand about Frenkel excitons in our hydrogenic model. Roughly speaking, again, you can even get this just by looking at where we expect this to fall in our map. If the binding energy is inversely proportional to the size, we expect relatively large binding energies. So for an organic semiconductor, we have a dielectric constant that's about 3 to 4. And then an effective mass in the numerator that is actually pretty difficult to measure and can be quite a large effective mass in molecular states are localized in space. That tends to mean that they're sort of spread out in k-space, which corresponds to a relatively large effective mass. So the best we can do for tetracene is to take a look at photoelectron spectroscopy data of the band structure of a related molecule called rubrene, which is just tetracene with 4 non-conjugated phenyl feet attached to the acene rod, if you want. And there you get a whole effective mass for rubrene that's about 0.65 times m. And so if we just go ahead and take that as a rough estimate of the effective mass that goes into the hydrogenic model, and we take the size of the molecule to be about a nanometer, then we get a binding energy for an exciton on tetracene that's about 0.28 electron volts. So that's a pretty large exciton binding energy, and it's mostly driven by the fact that the excitons are small, right? Dielectric constant is pretty smallish. Effective mass is, again, it's not huge, but it's also, we need, this is perhaps the biggest uncertainty in this entire discussion, is how do you understand the effective mass for these systems? Okay, so the intuition you're supposed to just take from this is that, yes, we get a relatively large binding energy. And you can go a little bit further and actually develop a full hydrogenic model for a related system of 1D conjugated polymers. And so Barford has done pretty extensive calculations over the years using the Hubbard model, or the extended Hubbard model, to understand exciton binding in conjugated polymers. So long chains where you have pz orbitals along the chain that can delocalize. And in that case, you get a hydrogen-like model where the numerator is now modified to have not only the effective mass, but also essentially one-dimensional band structure effects associated with the conjugated polymer chain. And so this is actually really interesting to me because it goes to show that, sticking with a hydrogenic picture can be really valuable and can be sort of extended in unexpected ways, even in very sophisticated calculations. I don't know about unexpected is the right word, but it can be extended in ways that you wouldn't necessarily guess would work, right? That you might think, well, it's just so complicated that you don't know how it should look, and it turns out to sort of work. So it's a pretty cool idea. But let's talk just more about language. And I want us to start with a picture of the ground state of an organic molecule. Let's say it's tetracene. So in the ground state, you have an orbital. That's this lower box where we have paired electrons of opposite spins. And then you have an unoccupied orbital that's the upper box. And we're going to imagine making an excitation into that upper orbital in just a minute. All right. But before I do that, I want to actually make a distinction about this ground state. I am describing this ground state by focusing on the frontier orbitals in this filled box and this empty box. So if you know a lot of chemistry, you know that I would call this the HOMO and the LUMO for highest occupied molecular orbital and lowest unoccupied molecular orbital. But I want to make a distinction between this ground state and the orbitals in the ground state. And so I'd like to describe this ground state, or this ground state configuration, as the S0 term symbol. We'll see why it's called S and 0 in a minute. All right? And just remark that the S0 state is not an orbital, right? It's a collection of orbitals that we choose to care about in our analysis. So for this, it's just the two, the occupied and the unoccupied. So now when we make an excited state, we take one of the electrons and just promote it into the unoccupied orbital. And this is going to be called an S1 term. And we're going to call that a singlet exciton. Right? And so again, one of the points that I want to make here that's just about terminology is to distinguish between terms or state symbols and the molecular orbitals that go into them. Right? The S1 state is a spin up electron in the occupied orbital and a spin down electron in the unoccupied orbital. Right, and so S1 is not the LUMO. It's not the lowest unoccupied molecular orbital. And you can sort of understand that because we're choosing to call S1 a singlet exciton, right? And that means there's something in this diagram that's missing. and that is the hole that we leave behind in the normally doubly occupied, highest occupied molecular orbital, right? When we make that excitation, it's just like we're going from the valence band to the conduction band. We leave something behind that somehow changes the Coulomb interactions within the molecule. And so this is the sort of exciton binding between this electron and the hole left behind here. And so this is not the LUMO, it's the singlet exciton state. It is worth sort of remarking that, because of Koopman's theorem, I guess you can say that the S0 state energy does turn out to be what you would think of as the HOMO energy. It's not really very important and probably needs to be modified if you're, there's probably a lot of caveats if you're a computational chemist. All right. So singlet, so we've got a ground state S0 and a singlet exciton first excited state. And this is the beginning of a Jablonski diagram. Our Jablonski diagrams, we're going to talk about drawing transitions between states. Again, not transitions between orbitals, transitions between states. So let's do a little bit more language associated with now what we're going to call a Jablonski diagram. So we've got our ground state and our first excited state, and when we talk about that transition from S0 to S1, that's what we call absorption, right? So light absorption means transition from S0 to S1. You could then imagine that excited state decaying back to the ground state with the corresponding emission of light, and that's what we refer to as fluorescence. It's also, I guess, what you would refer to as photoluminescence that we talked about in our previous lesson. So let's add a little bit to these Jablonski diagrams, and let's recognize that the ground state has a molecular potential energy curve that looks kind of like this blue shape. And if you look near the minimum energy geometry associated with the S0 ground state, it's sort of like a harmonic oscillator. And so you've got molecular vibrations that can occur around the fixed, the ground state geometry that correspond to different vibrational energy levels, right? Where the vibrational quantum number n can go from 0 up to infinity, and the energies of the different vibrational states are n plus a half h bar omega, where h bar omega is a vibrational quanta, right? And so now the ground state has a vibronic progression superposed on it that basically tells you how the structural fluctuations in the molecule modify the electronic energy of the molecule in very small ways, right? So this is actually the ground state of the molecule, the n equals 0 vibrational state. And a similar situation occurs for the S1 excited state. That excited state has a known geometry that's different than the ground state geometry, where we're just characterizing geometry by some generic reaction coordinate q, right? And so you have a vibrational progression superposed on the excited state as well. And so you now have transitions between ground and excited state that need to consider the vibrational state of the molecule. And so this is where we get the sequence that you saw in the Yamagata data in both the solution phase and the solid state data, where you have transitions from n equals 0 to n equals 0, from n equals 0 to n equals 1, etc., right? So that's what this vibrational progression is going to show. And there's just an infinite amount of discussion we can have about why the relative intensities are how they are. This is a really important physical chemistry topic, and I don't want to spend, we're just sort of laying out some of the language here. We're doing the zoology, and we're not really doing the in-depth physics discussion. But it's a really interesting topic. So yeah, we've got our vibronic peaks labeled by their oscillator quantum numbers. And one of the ways that you know that these are vibronic levels, and this can be difficult to figure out depending on the sort of specific data that you have available to you, but in this case it's fairly obvious. The relative intensities are important, but that's a complex topic. What's most important, just from a basic perspective, is that they're evenly spaced, right? So the spacing between 0, 0 and 0, 1 is the same as the spacing between 0, 1 and 0, 2, and that just comes from the fact that the spacing between vibrational levels is uniform. Okay? And so we'll occasionally, not always, but occasionally modify our Jablonski diagrams to show vibronic progressions on top of the heavy lines associated with the term symbols. And so it's most important if you really need to think about how to interpret those fine structures in your optical spectra. It can be important if you're kind of thinking about the impact of sort of creating a vibrationally excited state and watching it rattle down to the vibrational ground state. It's not super important for sort of distinguishing between different types of exciton. It's just a sort of language that you need to know in looking at data in papers. So let's keep going, talking about terminology. So we talked about this singlet exciton. And let me go back and just say the reason we're calling it a singlet is in reference to the spin of the state, right? So the spin of the electron is a half. The spin of the state in the ground state is 0. Because of Pauli exclusion, we're required to have opposite spins in the ground state. And then when you absorb light absorption itself is not, or let's say almost never, going to flip a spin, right? And so you maintain spin 0 in the excited state upon absorption. And so singlet ground state goes to singlet excited state. Singlet just means S equals 0. So spin multiplicity equals 1 for S equals 0. It is possible to imagine a triplet exciton where somehow, not directly by light absorption, but somehow, some way, you've been able to flip the spin in creating an excited state. And so the triplet exciton is different than the singlet exciton. It's another new species. So within the framework of Frenkel excitons, we have singlet excitons and we have triplet excitons. So we're sort of expanding our zoology all the time. Typically, the triplet is going to be lower in energy than the singlet. And that's because when spins are aligned, the electrons, on average, can be farther apart. This is just sort of another way of saying a Pauli exclusion principle. And so that means less electron-electron repulsion in this excited state. And so typically a lower energy. How do you make a triplet exciton? Well, I'll talk about it in the next slide, I think, but at this point it sort of doesn't matter. We're just laying out the language. But the important point is you don't create a triplet exciton directly by light absorption. And so an S0 to S1 transition is what's called spin forbidden. And that means it basically almost never happens. And that's an example of the spin selection rule. So how do you make a triplet exciton? You need to have some process called intersystem crossing. And so the idea is you're going to directly populate the singlet exciton by light absorption, S0 to S1. And then somehow you have to convert the singlet excitons into triplet excitons. And that's called an intersystem crossing. And it most often occurs due to spin-orbit coupling that the electrons in the excited state feel due to heavy nuclei in the material. So if you have like metal impurities, if you want, or if, for example, your organic compound has heavy elements like selenium, you might expect to have strong intersystem crossing. Another really good example is if you've got a metal phthalocyanine where the phthalocyanine is a 4-dentate ligand that surrounds a metal. The metal establishes a strong intersystem crossing that allows you to have S1 to T1 transitions. So if you do get an intersystem crossing, you can populate the triplet. And then the triplet can, of course, decay back to the ground state. And that's referred to as phosphorescence. And typically that's a slower process than fluorescence. Again, just because T1 can't directly decay to S0 because of the spin selection rule. You can't just emit a photon of light and flip the spin. All right, so there's a ton of discussion here. Like, I'm not really explaining or justifying any of these selection rules. This is all about terminology. We're trying to lay out what types of excitons are out there and what language do we use to talk about them. That's the zoology of this mini course, okay? You can spend a whole career on all of these topics. So here's some of our Jablonski diagrams where we label important things. We've got ground states, we've got singlet excitons, we've got intersystem crossing arrows, we've got triplet excitons. So when we're making a Jablonski diagram, we're talking about heavy lines showing term symbols for the various states. We've got a vertical direction labeling energy to show transitions between states. I mean, that's the thing we directly measure in spectroscopy is transitions in energy. And then in the horizontal direction, we're often showing the different spins of the excited states. So we'll sort of imagine intersystem crossing going horizontally here. Now here's just an example of some interesting photophysics you can talk about when you're using these Jablonski diagrams. So we show here in the case of pentacene and tetracene how this particular group is analyzing the possibility of what's called singlet fission. And so that's a situation where you absorb into singlet exciton states. You can have sideways transitions into sort of defective-like states that can then break apart into two triplet excitons, right? And so what is the point here? I mean, I think what they're trying to show is a particular proposal for how singlets can break up into two triplets via an intermediate, they're calling it an excimer state, and I'm not going to talk about excimers in this lesson, or maybe ever. So yeah, this is just an example of how you would use Jablonski diagrams, right? Where you're showing energy on the vertical axis, different types of states displaced horizontally, just to sort of schematically indicate the types of transitions that might happen in your system. Okay, so last terminology for this mini lesson, and we'll be done. I want to talk about this effect of Davydov splitting, which is kind of going to lead us into the next mini lesson where we talk about yet another species of exciton, yet another species of Frenkel exciton. And so we remarked that in the tetracene solution versus solid comparison, it looked like every peak was doubled. So if we had used unpolarized light instead of polarized light, we would have seen a superposition of the black and the red. And so it would look like the 0, 0 peak was doubled, the 0, 1 peak was doubled, the 0, 2 was, etc. Right? And so this is the effect of condensing tetracene into a solid state unit cell where there are 2 molecules per unit cell. So that's just a fact about the tetracene unit cell. And the idea of Davydov splitting comes from the following argument, that if you start with isolated molecules where you expect to have an S0 to S1 transition, and now you allow the isolated molecules to interact with one another, there's a shift, and that's just the energy shift between the dashed and, you know, the average black-red line. And in a solid, that shift will be different than just a dimer, but let's just think about a dimer for simplicity. And then what you can imagine is that within that dimer, there's not only like a rigid environmental shift, but maybe there's a little bit of excitation sharing between the 2 molecules, right? And that gives a very slight splitting. So the shift between the dashed and the black is large. The shift between the red and the black is small, right? So this is slightly exaggerated, but this splitting should actually be pretty small compared to the D-dimer shift, right? And so this idea that within a unit cell where there's 2 inequivalent molecules, that you get excitation sharing between them and an extra splitting is called the Davydov splitting. And that's going to lead us next time into thinking about, all right, yes, these Frenkel excitons are mostly localized on a molecule, but not perfectly, right? There's always going to be some leakage in a solid. And again, it's a specific solid state effect that only occurs for crystal structures where there are 2 molecules per unit cell, and that's not every crystal structure. So you'll always have some shift due to the fact that an isolated molecule now is in a different environment than it was in, say, the gas phase or the solution phase. And whether you get Davydov splitting is highly dependent on the type of crystal that you form. And this treatment is basically in chapter 6 of Schwerer and Wolf. And they go on, they start with the dimer analysis, and they do this in detail. I'm not doing any of the details here, as you can tell. They do the dimer analysis in detail, which is really nice. And then they also expand that to include a periodic solid, which is also very nice. So here's our summary. If you've got a molecular solid, you can have excitons localized predominantly on single molecules. And so these type of small excitons where the exciton size is not much larger than the lattice spacing are called Frenkel excitons. They have a large binding energy. And in molecular solids, you'll see really observable effects of intramolecular vibrations that are further evidence that these are fundamentally molecular excited states. And then there are minor solid state effects, such as shifts in the peak energies and Davydov splitting if you have 2 molecules per unit cell. And we also talked about the terminology associated with Jablonski diagrams, where you have absorption, intersystem crossing, phosphorescence, and then fluorescence I didn't draw, but that would be S1 back down to S2. Just a sort of way of talking about the different excitons and the different transitions in a molecular solid. All right, so that's all for this time, and the next lesson will be about a new species of exciton called charge transfer excitons.